Let's make a very brief introduction to the IDE, the Interactive Development Environment, the testing mode. This is again DB13, the Array43 Users Manual, and here is section 5. This is an introduction to and an explanation of the interactive testing mechanism. The second page of it goes into, actually starting at the bottom, and at the top of the second page is talking about how you get at different nodes in this environment, how you select which node you're talking to. It all depends on predefined paths which go through the chip. The paths are predefined this way, such that, for example, the default IDE path has path 2 going to every node on the chip except 708, which we're coming in on. And path 0 goes through all of the peripheral nodes, as in the edge nodes, which have potential I/O capability. Path 1 is free for you to define in any way you like. When one of these paths is in use, as in a connection is being actively made to one of the nodes on it, you can have some problems trying to cross paths with another one. So you want to be careful about that. Again, see the manual. But once we've selected a path and a node to operate on, we then can do various things to that node. These routing control things are fine points of what you can do with the path management. But here are operations you can do in the target node. UpD and .stk, for example, and C will show you what's going on in the node. Question RAM, question ROM for dumping RAM and ROM. Question stack for seeing the stack. -ASM will display a certain section of RAM or ROM that you give disassembled into code. With labels, if you've got the right bin set up for label provision. And lit, rfetch, rstore, these are all fetches and stores in memory, down to the actual F18 instruction set. All of these guys down at the bottom here execute single instructions, and you can see on the stack what the effect of them was. So let's see how this works in reality. If this is the first time we have spoken to this chip using this particular instance of the system, we need to tell it which port to use. If we locate the place where that is, we can do that by saying config list. This block here is the one in which the serial port is selected that we're going to use for communicating. Port 4 just happens to be the one which is going to be used for the, well, let's use a different chip. So 4, make that port 11. All right, COM port 11 will go into a different board that's not an eval board, but it's one that we can use. And it will be kind of nice because we can actually restore it, well, cycle its power and everything, which I just did. Okay, so we'll reload the system here to get this all made into effect. Reload. All right, and let's double check that that change we made took. Yes, see, here it is on line 11. That's port 11, a-com question mark, verifies that that's what's in it. So to connect to this board, we say host load. And then we say talk. And then we say C. And we are talking to node 707 using path 0. That's what's on its stack, see under UpD. And question RAM shows what's in its RAM. And it's all pretty much power up status. Now if we say 0300 hook, boom, we are now connected to node 300, which is 12 nodes away from us in the path. And if we say C there, well, we end up with something similar but not identical. All right, and that's because we've been in there and putting things in it. Now let's take a look at the stack. Let's switch to hex. This depiction of the stack shows the S register and the T register. T is the top of the stack effectively, S is the next underneath of it, and then this is the array of stack elements. We depict this as a circle, if you will. This is the first one that we'll push into, and the first one that will, well, it's the first one that we will pop. This one above it, which is the bottom, is the first one we'll push into. If we push something into here, this one will move there, that will move there, that will move there, that will move up, this will move to the right, this will move to the right, this will move to the right. So let's see what happens here. If I say 1.lit, why, we put a 1 into T and moved everything to the left. 2.lit, now we've got a 1 and a 2 in S and T respectively. 3.lit, and this is where we see the array doing its thing. Now we've got the 1 pushed into the stack array, right down here. And when we push a 4 onto there, boom, the 1 is moved to the left. Let's keep marching around. Let's do the rest of them. 5.lit, 6.lit, oops, helps to type correctly. 7.lit, 8.lit, 9.lit, and, oops, that was garbage. Our drop will get rid of that stack element. 9 dot space lit, boom, and 10 dot lit. And here we are with the 10 things that we've pushed onto the stack. And you can see where all of those things that we pushed onto the stack went, I hope, in that quasi-circular form. If we pushed another one, the 1 would be rotated down to where the 8 is, but would be clobbered by the 9. Let's see that happen. 11.lit. You see that the 1 would have rotated down to where the 8 was, but in fact the 9 clobbered it. And now if we pop that, our drop, you can see that the 9 has gone into S, and it also is rotated around to the bottom of the stack. And that's what we mean when we say that you can use that stack array as a convenient, non-addressed, but positionally and in sequence addressed set of variables or constants. It's kind of a neat thing. Saves you, it acts like a register array of sorts, but you can arrange so that constants are conveniently there when you need them rather than having to be picked up out of memory. You'll see examples of that in our code. At any rate, you just saw 2 instructions used. Lit basically is like a literal, and our drop is in fact the drop instruction. If I say RINV, lo and behold, look at that 10. The decimal 10 has been inverted to a 3FFEF, and I say RINV again. Lo and behold, there it is, a 10 again. And all of these things are sitting there. R2 star, now it's 20. R2 slash, and it's 10 again. So all of the F18 instructions you can do. You can also call a location in memory. You can put code in memory and call it and then see what it did. Additionally, by selecting the bin from which you know the code came that's in this node, you can do a nice job of disassembling it complete with a symbol table. For example, we know that this node 300's ROM code came from bin 300, and so if we say this decimal 300 using .sym, there is the symbol table for at least the ROM code, which is in this node. And now if we say hex, let's look at what's in 6IN. C0, 0C minus ASM. There is the code at 6IN and the code at 2IN. We see that C0 at 6IN calls C2 twice and then executes C2 by falling through into it. So 2N has been done 3 times by the time we're done and finally returned from 2N the last time. This is a typical technique for using our chip. At any rate, this is a disassembled dump of ROM content.